Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to talk about the different ways in which impacts are analyzed. So what I want you to imagine here, right here, we've got a pair of objects, and for this discussion imagine that they're identical other than the fact that one is red and one is blue. Imagine they're on a purely frictionless surface and that this red object is moving to the right at 10 centimeters per second. Now, I've already inherently given this a name here. I'm going to call this object A and this object B for the discussion here. And we're going to be looking at lots of problems where we're going to have multiple objects in multiple different time frames. I like to use letters for the different objects and numbers for the different time frames. So VA1 is velocity of this mass in what I'm calling picture 1. Now, imagine this red object here hits mass B and sticks to it somehow. Maybe they've got super glue here, or maybe they've got some Velcro or something. So that's going to be my picture 2. So we got picture 1, picture 2. It's important to realize that if mass A hits mass B, and remember there's no friction or anything in this example, this system now, both of them are going to be moving to the right. So I'm going to go ahead and draw a velocity vector for that motion. It doesn't really matter where I put it in the problem, but I'll go ahead and put it right here. Boom. And this I'm just going to call V2. It's important to note that that velocity is common to both of them. All right, and that's why I didn't bother with an A or a B. It's this, these things are stuck together. They're going to have the same velocity. Now, you know, in my physics classes, I usually set up an experiment here where we show this and actually get out the motion detectors. But, you know, I think most people watching this video, if I were to ask you what do you think the relationship is between VA1 and this V2, given that these are equal masses, I don't think it's too much of a stretch for most people to guess that V2 would probably be about 5 centimeters per second. And it turns out it would be pretty much exactly 5 centimeters per second. I think what I'll do is I'll make another video where I show an experiment like that. But for now, I'm going to ask that you take my word for it. So this velocity vector would actually have to be shortened up just a little bit. You know, we would want it to be basically half of this one, so that's good enough. All right, now we're going to take some time and we're going to use a velocity graph and think about the motion of these systems here. And we're going to take them one at a time. I'm going to start with the red mass. So the red mass was moving along at 10 centimeters per second. I'll just put a 10, and then half of that would be 5, and I'll put in units of centimeter per second. I'm going to go ahead and use my straight edge here and graph this. So the red object would be moving along at pretty much constant velocity until it hits that blue mass. And once it hits the blue mass, now its velocity is going to be cut in half. Very, very, very quickly. Something like maybe this. Now, this little time frame here would be very, very, very small. I'm actually going to go back now and redraw this and kind of exaggerate that time. It's important to realize that time would be awfully darn small, you know, 100th or maybe 1,000th of a second. I'm going to exaggerate it a little bit on my picture here, though. All right. So this small time frame, if I come straight down here, from here to about here, that's a very small, I'm going to call that a delta t. It's very important to realize that's a very small time. And the velocity of car A is changing pretty much only in that time frame, at least as far as it's changing as regard to its interaction with mass B. I mean, maybe we have friction and air drag or other factors, but throwing all of those out, the change in velocity due to it hitting mass B would be happening in this little delta t here. And we're going to assume that the velocity is constant from in the other times. All right. I'm also going to draw the velocity of the blue car. So the blue car didn't have a velocity in picture 1. It's just sitting there. So in this graph, this would be 0 up to this point. But then what happens is, in the same time frame, the blue car's velocity jumps. And now they have a common velocity. So I'm going to go ahead and even put that in my picture here. I'll just do this. Kind of put the blue and red right on top of one another. Boom. So the important thing to realize is what's happening in this time frame here. Now, It's the same delta T for the blue and the red. And I'm going to ask that you take my word for it in this video, but I'll go ahead and make another one here where I experimentally show this. It's really the same delta V as well. The blue, the delta V for the blue is plus 5 centimeter per second. The delta V for the red is also 5, other than it's negative. Rise over run, minus 5 centimeter per second. So the blue went up 5, the red went down 5. That means the acceleration of these lines are the same, at least within magnitude. The magnitude of the acceleration is the same because acceleration is delta V over delta T. Same delta V except the minus sign. Right? Now remember, these are identical masses as well. So if these are identical masses, what that's guaranteeing for us is that the net force on each mass is the same, because by Newton's second law, net force equals ma. They're the same they're the same masses. That's the basic principle, or my basic assumptions for this problem. And we just showed that they would have the same acceleration because the slopes would be the same. The only thing that would be different would be the plus and minus sign. Right? That has very important consequences for what's happening here. If we look at these things individually here, I'm going to go ahead and let's see, make one of these masses up. All right. And let's take a look at mass A here. So I'm going to color that red. If we look at the forces acting on that mass during the impact, and that's important, you know, we're talking about during that tiny little time frame here. I'm going to go ahead and put force vectors in here. Okay, we've got a gravitational force down. Oops, I'm going to go ahead and draw my force vectors in black. We got a gravitational force down, mg. All right, surface and contact, we have a normal, that would be up. And it's very important to realize that when these two are interacting, we're talking right in this time frame here, you'll notice that the red mass has a negative acceleration. If we're doing right positive, the acceleration is to the left, indicating the net force is to the left. So the other force that I got to get in there is the force that occurs between these two masses. And that force would be to the left on the red mass. And again, this is the force between them. I'll put NAB, the normal force between A and B. And that force is really only occurring over this small time frame here. All right, now we're going to think about mass B. So I'll create another one of these here. We'll think about what's going to be happening to this animal. All right. So we're going to have a gravitational force down. Mg. We're going to have a normal up. And again, that's due to this surface and contact right here. And very important to realize this normal force that occurs between A and B, it's left on mass A, or it's left on the red guy, but that same force is to the right on mass B. And whoops, I got a colored mass B there. There we go. And I'm going to go ahead and put that force vector in. Oops. Except I'm drawing my force vectors in black, so I'll continue to do so. NAB. So again, this picture is when they're actually in contact with one another. I know I've got some separation here, but I really shouldn't. I mean, you know, what I mean is that, let's see if I can actually get these guys together. So this is the free bodies of each mass while they're in contact. And again, it's important to know this, to notice this, that these normals only occur in, whoops, in this time frame. Those normal forces are responsible for the left acceleration of mass A and the right acceleration of mass B. And again, they're not there just before impact. They're also not there after impact. Once the impact has occurred, once we're out of this little delta t time frame, these normals, this one and this one, would be gone. Now, in one of my previous videos, I talked about momentum. And basically, momentum conservation looks like this. MV1, which stands for the initial momentum of a system, plus F delta t, which is any impulse acting on the system, equals MV2, which is your final momentum. And at the end of that video, I'd asked the question about, well, what if your net force was 0? Now, whether your net force is 0 or not depends on how you define your system. If our system is just the blue mass, look at those 3 forces. No way they can add to 0 because this thing's to the right. And look at if we define our system like this. Again, there's no way they can add to 0 because these 2 forces are vertical. We have this force to the left. There's nothing to cancel it out. But if we define our system like this, if that is our system, there is no net force acting on that system because these 2 forces add to 0. I'm going to say basically by observation. It's not accelerating up or down. Same thing with these 2. And these 2 have to be the same. Newton's third law, equal but opposite. Also, there's graphical evidence that they are the same. Remember, let's go back to our graphs here. Minus 5 over delta t for red, plus 5 over delta t for blue. These masses had the same acceleration in that delta t time other than the direction. And they had the same masses, remember. So by Newton's second law, F equals ma. If the a is the same, right, and that's indicated by the slopes being the same, at least in magnitude, and the m is the same, then the F is also the same. So these are the same forces. If we define our system like this, the net force on that system is 0, and that gives us a very, very nice equation here. MV1 plus 0 equals MV2. Now, I know that this system has 2 masses, but don't worry about it. For now, look at what this equation is saying. If I have a system and I know its initial momentum and there's no impulse, the final momentum is equal to the initial momentum. And that's the really key feature about momentum concepts. So I'm going to go ahead now and write a momentum equation here that describes this problem. Let's see, I'm going to get rid of this stuff that I don't need. All right, so what I'm going to do here is apply what's called momentum conservation, or conservation of momentum in the x direction. I'm going to call right positive. Now you'll notice I'm defining a direction and talking about positive. That's because momentum is a vector concept. Because momentum is a vector concept, it follows all the rules of vectors. All right. I look at my initial picture. I write down something for the total momentum of the system, which is going to be mva1. Remember, momentum is mass times velocity. Whatever this mass is times the velocity va1 represents the total momentum of this system. Mass b doesn't have a momentum because it's not moving. All right, picture 2. There's really only one velocity. My system here is both masses. So the momentum of that system, I could write it a couple different ways, but I could write it like ma plus mb, or I'll just do this, 2m, because they're identical masses and there are 2 of them, times v2. There's our final momentum, mv. And because of how we define our system here, the net impulse is 0. So there's no change in momentum, which means basically this. We can put equality between these. And again, very important. That's because net force on the system is 0. The net force on the red mass is not 0. Net force on the blue mass, not 0. But because of how we define our system, net force is 0, which means the momentums are equal. It's real easy to show that. Let's see, the mass divides out, and V2 is 1/2 of VA1, which in this example would be 5 centimeters per second. So the reason I made this video, or what I want you to take out of this, is mainly why we use momentum to analyze impacts. Because if we are clever about how we define our system, we can usually define it in such a way that the net force on the system is zero, which allows us to say that the initial momentum equals the final momentum of the system. Now, a lot of times there will be more terms on the left or right, but conceptually the equations are written that way, by looking at the initial momentum and setting it equal to the final momentum, if in fact we can define a system where the net force is zero on it. Hope this video helps demonstrate these concepts. Have a great day.